My name is Mpho Mashika and I'm a student at the University of Johannesburg. This is a presentation for my final year research project. My research was about finding a way to automatically detect cough events based on audio signals in a non-invasive way. Cough is one of the most common symptoms of respiratory and lung diseases such as asthma, rhinitis, and pneumonia. Because cough events convey vital information of the state of the respiratory system and the status of the disease progression, larger scale cough detection plays an important role in epidemic prevention and control, epidemiological research, risk assessment of infectious diseases, and other fields. For example, the World Health Organization confirmed that the primary symptom of a patient with COVID-19 is cough. Therefore, large-scale and contactless cough detection applications are of great importance. The occurrence of cough is usually accompanied by the production of some specific sound. We therefore used audio signals to build a model to achieve remote detection of cough events. To train our model, we use data from the ES50 dataset. We took 385 cough samples and 385 non-cough samples and did a 4:1 split, with 80% of the data used for training our model and 20% of the data for testing our model. Before using the audio to train our model, we had to perform some pre-processing steps. The first step is pre-emphasis. An audio signal may have frequency components that fall off at high frequencies. To avoid overlooking the high frequency components are compensated using a pre-emphasis filter. The next step is framing. Framing splits the signal into sufficiently short segments such that each segment contains only one phenome. Windowing functions are smoothing functions after framing so that there are no discontinuities at the points where we actually cut off our signals. The features we used in this study are the male frequency septal coefficients, zero crossing rate, and the short-term energy. After our pre-processing of the audio signals, we apply the fast Fourier transform to convert the signal from time domain to frequency domain. For audio signals, analyzing the frequency domain is easier than time domain. Next, we convert from linear scale to mel frequency scale using mel filter bank. The way our ears perceive sound is different from how machines perceive sound. Our ears have higher resolution at lower frequency than at higher frequency. So, if we hear sound at 200 Hz and 300 Hz, we can differentiate it easily when compared to sounds at 1500 Hz and 1600 Hz, even though both had a difference of 100 Hz between them, whereas the machine resolution is the same at all frequencies. It is noticed that modeling the human hearing property at the feature extraction stage will improve the performance of the model. So we use the mel scale to map actual frequencies that the human will perceive. The MEL filter bank consists of a number of overlapping triangular filters, such as the one shown here. At the last step, we apply the discrete cosine transform to the output from the previous step, and that gives us the MFCC character vectors. Other features we experimented with include the zero crossing rate and the short-term energy. Classification. The classification we used are the SVM, KNN, and the multi-layer perceptron. SVM works by trying to draw a street between the classes it is trying to classify. If you have a red classes, then blue classes, SVM will want to draw a street as wide as possible, so that way it knows that every point that falls on this side is the blue class, every point that falls on that side is the red class. But things are not always this simple. Consider the input space here. It is not easy to draw a street here, but that does not necessarily mean we can't use the SVM. In fact, what we can do is we can use a kernel trick to actually transform this from this this data from one-dimensional space to a higher dimensional space. This way we see that we can draw a street across this data quite nicely. Other classifiers we considered include the KNN classifier and the multi-layer perceptron. We provide a summary of our model and other experiments that we considered during the study. Our best performing model was the MFCC paired with a support vector machine classifier, achieving an accuracy of 92.2%. Now to demo our actual project. I've already loaded in a file from our test sample. Now I'm gonna see its signal. This is its signal. Okay, this may be not the best example. Let's open another file then. Okay, this has a better signal, a less noisy signal than the previous one, so it's easy to actually see the pre-emphasis. Okay, you see here we have components that fall off at high frequencies and some at very low frequencies, but after pre-emphasis we've compensated those components and actually kind of balanced the signal. And then we have framing, which we actually cut the signal into segments, and then we're going to apply windowing here and this discontinuities to smooth it over. Okay, then zero crossing rate. Zero crossing rate tells us on average how many times per frame does the signal cross the zero line. And here we see that from 0 to 10, for the first 10 frames, the average zero rate is 0, which tells us that there is noise, there's silence between that period, and here we see that there's a lot of activity going on from frame around 15 to frame 40. There's a lot going on there. Okay, and now to play now classify that is indeed a file. One more file. Let's classify that one. That is not a cough.